Okay, today we're in section 7.4 in your book, and we're going to be applying our work with ratios and continuing on that, and really working with two big ideas that are not going to be very difficult for you. The first of which is on this page here, the idea of proportionality along the sides. So what we're saying is along this side, if AE is proportional to EB, because if these lines are parallel, then on the other side I must have proportionality as well. In other words, AF to FC must be that same ratio. Okay? That's it. We're basically just talking along about proportionality along the sides if you have a triangle inset and another triangle, if you will, with these parallel lines. The other side of that down here at the bottom is all we're saying is, guess what? If AE is to EB is the same as AF to FC, if those ratios are the same, then these lines here, EF and BC, must be parallel. Okay? And that's it to start this thing. All right, let's go ahead and move into some examples. And the examples are really nice. I think you'll see this pretty quickly and easily. I don't think this will be a big deal for you. So along this side here, if we've got 12 is to 16, and I've got parallel lines marked here, then I can say on the other side, well, x is to 24. This side here, x is to 24. The partials on both sides, if you will. So 12 is to 16, we're going to make our life a little bit easier here and say, well, that's 3 is to 4, just so I can deal with smaller numbers. No other reason, right? And I can say that because 4 goes into 12 3 times and into 16 4 times. So I get 4x is 3 times 24 is 72, and x equals 18. Let's go ahead and put it back in and take a look here. 12 is to 16 is 18 is to 24. Does that seem to fit in your math brain? I think it does. And let's move on. All right, we're going to do a few of these examples in this setting here, because you got to be careful as far as the setting here. So we've got on this side, we've got parallel lines. So I know I have proportionality along the sides. Okay, like that. I'll just get rid of that real quick, but just to kind of demonstrate dramatics there. So we got 12 is to 5. Okay, the partials on this side is the same as 15 is to x, the partials on the other side. Okay, and I know that because the lines are parallel. I can do that. So 12x equals 75, and x equals, let's just call that 6 and 3/12, which is 6 and 1/4 this time. We'll just use that as a mixed number this time. I'm going to kind of vary how I how I express these for you, just to give you a few different ways of doing that. And for y here, we're going to go ahead and say, well, the bottoms here, so let's go ahead and compare 10 to y. Those are corresponding sides. So 10 is to y as, we could say 10 is to y as, okay, let's match these sides over here. 12, which is the whole side in this triangle. So 10 is to 12 as, or 10 is to y as 12 is to this whole side here, which must be 17. So the bottoms 10 is to 12 as the sides 12 is to 17. So 12y equals 170, and divide that out and you get y equals 14 and 2 left over, so 14 and 2/12, which is 14 and 1/6. Okay, no units there, so we can keep going. Okay, now this guy right here, right away, if they're gonna label this whole side as 35, I'm gonna put this in as 25, so I know that I have the pieces that I need. So solving for x, So on this left side, 25 is to 10, as 30 is to, well, this is a little piece here, so x. And I'm going to go ahead and make this 2.5 to 1, simplify that a little bit, equals 30 to x, and 2.5 x equals 30, divide it out, and we get x equals a nice even 12. Well, does that make sense? 25 is to 10 as 30 is to 12. Yeah, that works. All right, that ratio holds. All right. And one more kind of exercise we can do with this idea is basically determine, are the lines parallel? Well, if these lines are going to be parallel, right here, these red lines, then I must have proportionality along the sides. So let's see. Well, on the left side, I've got 6 is to 5, and on the right side, I've got 5 is to 4. And I don't think that's going to work. So cross multiply 6 times 4, I get 24. Cross multiply the other way, 5 times 5 is 25. Those are not equal, so therefore I do not have proportionality, and I can say something like uh, segments, the segments are not parallel because the sides are not proportional. Okay, fair enough. All right. So let's move on here, and we're to our next idea, which is just an expansion of this same idea. Nothing has changed here, except I don't have a triangle as my picture. Okay, I've still got proportionality along the sides, but I just don't have it capped with a triangle. I've got three sides that are parallel here, and they're marked as such. And basically, we're still going with the idea of 8 is to 3 on this left side, as 10 is to x here. Nothing has changed here, so basically I got 8x is 30, and x equals, let's call this 3.75 this time. 30 divided by 8. Okay, but no, I mean, it's the exact same idea, though. We've got proportionality along the sides, and our picture has just changed just a little bit. We've gone from a triangle to three parallel lines. Okay, now we can use this idea here in this word problem to find these unknown sides over here. Let's go, we're looking for, which ones do they want? LM and MN. Okay, so the assumption we're making here is these trees are parallel to each other. The red lines are parallel. And if I make that assumption, then basically I can set up a couple of ratios here. I can go ahead and set up right here for LM, which is down here. I can say, well, uh, this is to this here, so LM to 4.9 must be the same as this is to this. BC, which is 2.6, is to AB, which is 4.5. Okay. Solve that proportion there to the nearest tenth. 4.5 LM equals, I think that's 12.74. So LM, I got like a 2.83, and to the nearest tenth, it's approximately 2.8. Okay. All right, let's go ahead and do the same thing for MN, which is right here. So MN, let's do with sides we know. MN is to KL, which is still 4.9, as on the top side of this thing, CD, which is 4.1, is to AB, 4.5. Just using matching parts there. Okay, so let's see here. Cross multiply, and we get 4.5 mn equals 20.9, 0.09, excuse me. And when I divide that out, I get mn is 4.46, and to the nearest tenth, that's 4.5. Does that make sense? When you just look at those ratios, 4.5 to 4.9, about the same as 4.1 to 4.5. Yes, that works. All right. Our second big idea is very simple. It's the idea that if I have a triangle, one triangle with an angle bisected at the top, then we got proportional lengths on the other two sides. So BD to DC is the same as AB to AC. Okay? So it's going to be very simple for you. It's not going to be a problem for you. So when you see an angle bisector here, let's move to these examples. They're pretty quick and easy. So I'm going to go, let's see, how did I set this one up? We got, so let's go, this is to this, so x is to 14 is the same as these end pieces. So 6 is to 9. Okay, 6 is to 9. Well, again, I'm going to make my math life a little bit easier. So x is to 14 as 2 is to 3. Just simplifying the right-hand side. And I get 3x equals 28. X is 5 and 3/5. 28 over 5. Okay. Last couple here, actually the last one. That's there's not much more to this. The last guy here, we got a very similar picture. Only difference is our x is on the end piece now. So we've got, let's start here and go 5 is to 15. As I got to go in the same spot, 4 is to x. Make our math life simple here. 5 is over 15 is 1 over 3. So x is 12. So what can you do today? You can do basically two things. You can apply properties of similar triangles here in this setting where you've got an angle bisected inside one triangle. So these opposite sides are proportional. And you've also got this idea of, at the very beginning here, let's go back to that picture real quick. If a line is parallel to the side of a triangle, it intersects the other two sides, then it divides those sides proportionally. In other words, proportionality along the sides when you've got parallel lines. Okay? Thank you very much. Hope you're having a great day, and we will talk to you soon.